Okay, this is Dr. Brown. In this video, we are going to look at a topic called implicit differentiation. Implicit differentiation allows us to take the derivatives when the function is described by an expression, an equation, not by an explicit y equal f of x. Notice in both of these examples here, x squared plus y squared equal 25. We know that from college algebra to be an equation that gives us a circle of radius 5. The second equation here gives us a parabola that is rotated 90 degrees. Notice that y equal f of x is not explicit. Sometimes you can solve for f of x, but sometimes you can't. So if you're given an expression as opposed to an explicit equation for f of x, how do you calculate dy dx? So how to calculate dy dx? In order to approach this concept, I wanted to give some examples of explicit differentiation. Explicit functions are like y equal x squared equal f of x, y equal sine of x equal f of x. All of these we can take the derivative of, and we have formulas and strategies for calculating the derivative. In each of these cases, dy dx is equal to ddx. For instance, of the first one, x squared. We're taking the derivative with respect to x, and what we see are terms involving x. Dy dx for the sine function we're taking the derivative with respect to x, and all we see is a function of x. Now, suppose I ask you what ddx of y squared was. Notice you don't explicitly see the x variable. All you see is y squared. Well, we know how to take the derivative of y squared with respect to y. We also have learned the chain rule. So one of the first things we're going to do here is caution you if the variables don't agree, you want to do this. You take dy of y squared and then multiply by dy dx, which is a chain rule. So, if we see y squared, we take the derivative with respect to y, which is 2y, and then multiply by dy dx, and in this particular case, that's as far as you can go. Later on, we'll be doing this when we're doing implicit differentiation, and we'll be able to solve later for dy dx. For instance, d dx of y cubed is 3y squared dy dx. Don't forget to multiply by dy dx. We know that y is a function of x, but we are not given the explicit relationship. So let's look at what the process will be in doing implicit differentiation. The first thing you want to do is write the equation. In fact, it could be x squared plus y squared equal 25. Write down the equation. Then we want to calculate d dx of both sides of the equation. So we want to do d dx of x squared plus d dx of y squared equal d dx of 25. Now, d dx of x squared is 2x. d dx of y squared is 2y dy dx. And d dx of 25 is 0. Now notice we use the chain rule to calculate d dx of y squared. And then we want to group all the terms with dy dx on one side and all the other terms on the other. Well, in this particular simple example, we have 2y, let me erase this here, 2y dy dx is a term that contains dy dx, and we'll move the 2x to the other side, and now we'll solve for dy dx. dy dx is just simply minus 2x over 2y equal minus x over y. So we have solved for dy dx using this process. And this is what you will do for all of the problems involving implicit differentiation. So let's do some more examples. Let's find dy dx for the expression y squared x plus x cubed plus sine of xy equal y squared. So we're going to follow the process. We're going to take d dx of both sides. So that's d dx of y squared x plus d dx of x cubed plus d dx of sine of xy equal d dx of y squared. So following with this process, we have a product here. So we would take the first times the derivative of the second, that's d dx of x, plus the second, which is x, times d dx of y squared, plus d dx of x cubed is 3x squared, And now it comes to d dx of sine of xy. So we have to realize that d dx of sine of xy is going to be cosine of xy times d dx of xy. That's the chain rule. And we're going to have to come back and use the product rule. And then for the right hand side, d dx of y squared is going to be 2y dy dx. So following on through here, we get y squared d dx of y squared is going to be, first of all, we'll put the x there, times 2y dy dx plus 3x squared plus cosine of xy. And now the product rule is going to be the first times d dx of y, which is dy dx, plus y times d dx of x. Of course, that's going to end up being 1. And on the right hand side, we get 2y dy dx. And I'm going to start collecting all my dy dx's. In fact, however, before we do that, let's just do this. Let's do y squared plus 2xy dy dx plus 3x squared. I'm going to distribute the cosine of xy, and I get plus x cosine of xy times dy dx plus y times cosine of xy. Notice that d dx of x is just 1. And so then that equals 2y dy dx. Now I'm going to actually erase some of this, and up here I'm going to collect all my dy dx's, and dy dx. The first dy dx I have is 2xy. The next one I have is x cosine of xy. And the other one I have is on the right hand side of the equation, so I'll bring it to the other side, and it'll be 2 minus 2y dy dx. So factoring the dy dx out, I have this expression. And now all the other terms go to the other side. And that's going to be y squared going to the other side is going to give me minus y squared minus 3x squared on the other side minus y cosine of xy. So now I can solve for dy dx. And I'll erase a little bit here, so I'll have room to write down dy dx. Dy dx is now this term divided by this, which is minus y squared minus 3x squared minus y cosine of xy, all divided by 2xy plus x cosine of xy minus 2y. And there's the answer. Now we have another problem here. We want to find dy dx for the expression. Actually, we'll find that this is a little simpler. What I'd like for you to do is you all try. Why don't you pause the video and try to work this problem, and then come back and see if you got the same answer. Okay, if you're back, we're going to take d dx of y cubed plus d dx of x cubed plus d dx of sine of x equal d dx of y squared. First term becomes 3y squared dy dx. d dx of x cubed is just 3x squared, and d dx of sine of x is cosine of x. And d dx of y squared is going to be 2y dy dx. Now, I'm going to collect all my dy dx's, and I'm going to get 3y squared dy dx minus 2y dy dx, and everything else that doesn't have dy dx goes to the other side. And now I can factor dy dx out. Dy dx times 3y squared minus 2y equals minus 3x squared minus cosine of x. And solving for dy dx, we get minus 3x squared minus cosine of x divided by 3y squared minus 2y. And if you want to, you can factor a y out of the denominator and get y times 3y minus 2. And this is dy dx. Now, getting back to a problem we have already done partially. This is the implicit equation x squared plus y squared equal 25. It's a circle with radius of 5. We're asked to find the slope of the tangent line at the point 3 and 4. And that'll be about right there. Now, I'm going to repeat the derivation of calculating the derivative. taking d dx of both sides, we get this expression. And d dx of x squared is 2x. d dx of y squared is 2y. dy dx. d dx of 25, of course, is 0. And you'll recall that we solved dy dx is minus x over y. Solving for dy dx. Now, to find the slope of the tangent line at the point 3 and 4, we calculate dy dx, x equals 3, y equals 4. Plugging in, we get minus 3 over 4. So the slope of the tangent line is going to be minus 3/4. So we can immediately write that y equals minus 3/4 x plus b, and we need to plug in 3 and 4 to calculate what b will be. So we get 4 is minus 3/4 times x plus b, and you can see that b is equal to 4 plus 9/4 equal 25/4. So the equation of the tangent line is y equal minus 3/4 x plus 25/4. And on the next page, I have the tangent line graphed in, and its equation is minus 3/4 x plus 25/4. Now on the next page, we have another implicit equation, y squared equal x squared plus sine of xy. Now, if we didn't have the sine of xy, we would just have y squared equal x squared, and we would have two equations, y equal plus x, y equal minus x. And then the graph would just be two straight lines intersecting one another. Obviously, the wavy pattern is provided by having to calculate sine of xy. So I'm going to erase this, and now we're going to calculate the derivative of y with respect to x for this expression. In fact, if you would like to, you can pause the video and give it a go yourself. So let's write this down. d dx of y squared equal d dx of x squared plus d dx of sine of xy. Doing this operation, we get 2y dy dx equal d dx of x squared is 2x, and d dx of sine of xy, we did part of this a minute ago. That's going to be, of course, cosine of xy times, using the chain rule, d dx of xy. So we get 2y dy dx equal 2x plus cosine of xy. d dx of xy is going to be, using the product rule, the first times d dx of y, which is dy dx, plus y d dx of x, which is just 1. And so simplifying this, we get 2y dy dx equal 2x. Distributing the cosine of xy, we get plus x cosine of xy dy dx plus y cosine of xy. And now I want to collect all of the dy dx's, and I'm going to go ahead and factor out dy dx in those terms, and I'm going to be left with 2y taking this over to the other side, I'm going to have minus x cosine of xy equals 2x plus y cosine of xy. So finally, dy dx is 2x plus y cosine of xy divided by 2y minus x cosine of xy. So here is dy dx for this expression. Okay, for this problem, we want to find the tangent and the normal line at the point 2 and 4 for this implicit equation. So using the same procedure as we've used before, we get ddx of x cubed plus ddx of y cubed minus 9 ddx of xy equal ddx of 0, of course, which is 0. ddx of x cubed is 3x squared. ddx of y cubed is 3y squared dy dx. And then we're going to have minus 9 ddx of xy using the product rule is going to be x dy dx plus y times ddx of x, which is just 1, equals 0. So simplifying this, we get 3x squared plus 3y squared dy dx minus 9x dy dx minus 9y equals 0. So now let's collect all our dy dx, and factoring dy dx out, we get 3y squared minus 9x, and we're going to send everything else to the other side, so the minus 9y becomes plus 9y. The 3x squared becomes minus 3x squared, and we now can calculate dy dx is 9y minus 3x squared over 3 times y squared minus 3x. See, I factored a 3 out. In fact, I can factor another 3 out up in the numerator. So finally, we can write that dy dx is equal to three y minus x squared over y squared minus 3x. So this gives us the derivative or slope of the tangent line at any point x and y. And on the next page, I'm going to calculate the equation of the tangent line and the normal line. So go ahead and let's write dy dx that we had calculated before. Dy dx is 3y minus x squared over y squared minus 3x. And to get the tangent line, we need to calculate dy dx at the point 2 and 4. And so that gives us 3 times 4 minus x squared, which is 2 squared, divided by y squared, which is 16, minus 3x, which is 3 times 2. So we get 8/10, which is equal to 4/5. So this is the slope of the tangent line. So y is equal to 4/5 x plus b, and we need to plug in 2 and 4, and when we do that we get 4 equals 4/5 times x plus b. So b is equal to 4 minus 8/5, which is 12/5. So the equation of the tangent line is y equals 4/5 x plus 12/5. And that would be this line right here. Now, the normal line the slope would be the negative reciprocal of the slope of the tangent line, which is going to be minus 5/4. So the normal line is going to be y equals minus 5/4 x plus b. Plugging in 2 and 4, we get that 4 equal minus 5/4 x, which is 2, plus b. Solving for b, b is equal to 4 plus 5/2, which is equal to 13/2. So now the equation of the normal line is y equals minus 5/4 x plus 13/2. And so the normal line would be perpendicular to the tangent line and would look something like that. Now, why don't you pause the video after we talk about this particular problem. You want to find the tangent and the normal line at the point 1 and 1 with the equation described by y squared times 2 minus x, parentheses, equal x cubed. So pause the video, try to work this problem, and again come back and take a look, see if you got the same thing. Okay, the first thing we're going to do is we're going to expand, distribute the y squared, and we're going to get the equation is 2y squared minus xy squared equal x cubed. And now we're going to take d dx of both sides. So d dx of 2y squared minus d dx of xy squared equals d dx of x cubed. Performing these operations, we get 4y dy dx. For this term, we have to use the product rule, so it's going to be minus x d dx of y squared minus y squared d dx of x, of course that's going to be 1, equal d dx of x cubed, which is 3x cubed, 3x squared. And now, simplifying all of this, we get 4y dy dx minus x d dx of y squared is going to be 2y dy dx and then we're going to get minus y squared equals 3x squared. Now, collecting all our dy dx terms, we're going to get dy dx times 4y minus 2xy equals 3x squared, and bringing the minus y squared on the other side gives us 3x squared plus y squared. And then solving dy dx is 3x squared plus y squared divided by 4y minus 2xy. And now we have an equation that can give us the slope of the tangent line. And looking at 1 and 1, dy dx at x equal 1, y equal 1. Plugging in, we get 3 plus 1 over 4 minus 2 equal 4 divided by 2 equal 2. So the slope of the tangent line is 2. So tangent line y equal 2x plus b. Plugging in 1 and 1, we get 1 equal 2 plus b, or b equal minus 1. So the tangent line is y equal 2x minus 1. That would be this line. And the normal line slope is minus 1/2 would be the negative reciprocal of the slope of the tangent line. So the normal line is y equal minus 1/2 x plus b. Plugging in 1, 1, we get 1 equal minus 1/2 times 1 plus b, which means b is equal to 3/2. So our normal line is going to look like this, and its equation is going to be y equal minus 1/2 x plus 3/2. So that is a video on implicit differentiation. We'll be talking about this in our next class.